Okay. Unlike Alan, who was not Aaron, I am Mark. And I'm here representing a large group. Just forgot about my glasses. This is what happens when you get to be my age. A large group of master's students and PhD students who have been working over the course of Metal Earth in a project we call Metal Oceans, which is trying to identify at a finer scale the different geodynamic elements of crustal growth. So we all talk about geodynamic elements, we all talk about rifts, we talk about half grabens, we talk about microplates, triple junctions, transforms, but we all have an idea about what they might look like. But what we wanted to do with this project was create a bona fide atlas of actual occurrences of these different geodynamic elements. And this is what my students have been working on, and many of them have graduated and moved on now, but as part of the synthesis volume that is being prepared, we're going to be generating this atlas of type localities. The area that we've been mostly interested in, of course, Alan already talked a little bit about it, is the edge of the Indo-Australian margin, focusing particularly on about a 1,000 kilometer by 1,000 kilometer box around the northern Lao Basin. We're also working in other localities now, which I'll talk about in a few moments. The focus has been on this major region of crustal growth, which in addition to intense magmatic and tectonic activity is also a region based on seismic velocities of some of the hottest mantle on the planet today. If there is an analog of Archean hot crust and hot mantle, this is probably it for the planet. And it's dominated by what appears to be the beginnings of a superior-sized continent emerging from the oceans. And that's the scale that we've been working on. Initially, we started mapping at 1 to 1 million scale, and we now have a series of maps that run all the way up to Papua New Guinea. And most of the students that have been working with us have been looking at specific geodynamic elements. We've seen the outline of the Abitibi many times, and here's the Abitibi Greenstone Belt rotated on its side. Fits exactly in the back arc basin of the Lao Basin, and quite unexpectedly and quite randomly, many of the structures that we recognize in the Lao Basin, such as the Peggy Ridge Transform and the Lao Extensional Transform Zone and spreading centers, they align more or less at the right scale with many features that we see in the Greenstone Belt. So one of the things that we were trying to do was to identify what pulses of crustal growth look like. The number one correlation between ore deposits and geodynamics is pulses of crustal growth. What do they look like? What are the probable time and especially the space scales? And we were quite nervous at the beginning of all of this process because the time and space scales seem to be a little bit different from Archean cratons and Archean greenstone belts, but this is changing now as we map at higher and higher resolution. Can we recognize anomalies in the crust or in the mantle that correspond to those pulses of crustal growth? And what types of ancestral structures could potentially be preserved in greenstone belts that could then be recognized? And that's some of the work that Keaton is actually starting to do. So as I said, we're working at a province scale, so the superior province would fit basically in this space right here, and the Abitibi Greenstone Belt could correspond to any one of these marginal basins along the Indo-Australian margin, all the way from the Lao Basin all the way to easternmost Papua New Guinea. We're putting together effectively lithostratigraphic assemblage maps of these different areas. This is frankly, it's a brand new approach. It's not been done in the oceans before, and some of you have seen some of the maps that we've been producing, which are true lithostratigraphic assemblage maps. These have now been published. Two of them have been published, one in Geosphere and one in Lithosphere. And these are free to download if you're interested in plastering it on your wall. It makes nice wallpaper. And you can download it for free. Here's the map that we've shown many times now. This is our very first 1 to 1 million scale map of the Lao Basin. It's remarkably robust considering no one has ever made a map like this before, and we keep going back to it, but you know, over the course of 5 or 6 years now, we've never really been compelled to make any changes. And that is a testament to the people who created this map. And we have two styles of maps. We have the lithostratigraphic assemblage maps. This would be equivalent to an assemblage map in the Abitibi, for example. And then the formation maps, the volcanic and sedimentary formation maps. It's within this context here, the formation maps, that we can begin to identify geodynamic elements that we want to be able to compare or potentially identify in preserved greenstone belt crust. One of the fundamental sort of frameworks for the work that we're doing is the microplate modeling. And Alan's done quite a lot of microplate, actual dynamic modeling of microplates in the northern part of the Lau Basin. And we've been modeling one of the largest microplates in the northern Lau Basin, which is basically this box right here called the Nuafo'o microplate. And we've been looking specifically at the edges of the microplates. We think that these are probably, several people have asked me, looking at a map, a piece of the Abitibi greenstone belts, and have asked me, is this a microplate? And my feeling is that we're probably not going to be able to see the entirety of any microplates, but what we can find are the edges of the microplates. And so what we have attempted to do is be pretty specific about mapping the edges of microplates. And one of them that we have focused on a lot is called the Phonolai Rift. And that's this object right here. You can see the yellow dots and the red dots, which are hydrothermal vents. And it represents the emerging eastern boundary of the Nuafo'o microplate. What you need to understand about the microplates is that they are basically non-rigid objects that are constantly deforming at the edges of these larger plates like the Pacific and the Indo-Australia plate. And we wanted to know what that edge looks like because it's the microplate edges that probably we're going to be interested in. And so we conducted actual transects, exactly like the metal earth transects on the ocean with seismic reflection, seismic refraction, magnetics, gravity, and magnetotellurics, which is something I'll touch on in a few moments because some new data are coming out on that. I was quite pleased to see that from Chris's work, this is the Bouguer anomaly of that area, which he has used in his gravity inversions, but we're able to identify many of the different assemblages within the different domains of the Lau Basin simply based on their gravity signal. Alan and Chris have now already shown this really spectacular map of the crustal thickness in the Lau Basin, which is now published, showing the microplate architecture and many of the rifts, some of which we couldn't see when we were doing our original mapping. For example, there's probably a new rift which is opening up below the sediments in the central part of the Lau Basin. That would be the new southern margin of the Nuafo'o microplate. And as we've already heard, there are many similarities at the same scale between this emerging rift architecture or microplate edge architecture and what Alan has just talked about in the Abitibi. Zooming in on the Phonolai Rift, that's this object right here, which is the new boundary of the Nuafo'o microplate. It's a propagating rift. It's basically a definition of the formation of a microplate. You must have at one time had a propagating rift, and that's exactly what is shown here. At the very southern tip of the Phonolai Rift, you can see density anomalies which correspond to new magmas that are being intruded into the rift, and the crustal thickness which shows the pointy end, actually two, of the very southern tip of the propagating rift. The seismic data, the reflection and refraction data, which I've shown previously, is illustrated here. Here's a cross-section through the Phonolai Rift. There's the Phonolai Rift running right down, and the propagating tip is right here. On the far side of the Nuafo'o microplate is what's referred to as Peggy Ridge, which is a crustal scale shear zone. leaky transform, and those are basically the two boundaries of the Neophoto microplate: a propagating rift on the east side, and a leaky transform on the west side, which is has over the last 5 to 7 million years accommodated most of the opening of the northern part of the Lau Basin. This is the velocity data, which shows you an excursion, a significant excursion of about 5 kilometers in height in the Moho, immediately beneath the Fonolai Rift. This is the manifestation of the emergence of the microplate edge. And here's the same image without the 3D effect, and it shows you this very large excursion in the mantle immediately beneath the Fonolai Rift. Some other interesting things here. You'll see that the lower part of the crust is actually quite heterogeneous in terms of its velocity structure, and we interpret this to be a wide range of different crustal elements that become part of the microplate, including extensive intrusion of gabbros and so forth that must be in that part of the crust. This is some new data which is being interpreted by Marian Yagan, one of our colleagues at Geomar, and during our transects we deployed about 20 ocean bottom magnetotelluric sensors. So this was one of the first attempts to do an MT survey on the ocean floor in a rift environment. There have been other attempts to do this. It's quite complicated, but I think in cross-section the main thing which impressed me is that the low resistivity anomaly immediately under the extension of the faults on the western margin of the rift looks an awful lot like the low resistivity anomalies that I've been seeing that I saw yesterday. Marian has interpreted this low resistivity to be due to pore fluids, interconnected pore fluids. And I said, fine, that's great. And my feeling is that this is telling us what some of those anomalies in the Archean might have been like. Maybe they're very early. We haven't even got spreading yet here. This is just the initial stages of rifting, and already we've acquired a resistivity structure which looks an awful lot like what you see under the Larder Lake Cadillac Break or the Dester Porcupine. And maybe some of these anomalies in the Archean are being inherited from very early history of those structures. I don't know, it's not my business. Maybe you can tell me. The elements, the geodynamic elements that we're mapping in detail or have been mapping in detail are quite diverse. They include rifts, they include transforms, they include microplates, they include triple junctions. If we can recognize these features, then we can begin to be more confident about the microplate architecture that's been discussed in terms of the Abitibi. So this is what we're mapping. Features that we're mapping, there's at least, I'm not going to go through them all, there are at least a dozen different things that we can identify that have different structural characteristics, they have different petrological characteristics. Mark Fassbender published a couple of papers in economic geology over the last couple of years that characterize the petrology of these different environments. When we brought Keaton on to try and tell us what these things look like in the greenstone belts, he said, don't be ridiculous, I can only look at one. And so he's now currently looking at the possibility of identifying triple junctions, which are a requirement of microplate formation. Every time you make a microplate, you make at least 2 triple junctions. It's unavoidable. And so we want to know what they look like and have been trying to map. This is an example of the Mangatolo triple junction in the northern part of the Lau Basin, at the same scale as the easternmost Blake River. And you can see some things that were even a bit of a surprise to me, which is, of course, the scale of the triple junction forming process. These are huge magmatic centers. The magmatic center, volcanic center in the Mangatolo triple junction is hundreds of cubic kilometers of melt. And that has to be what these represent and what we have to be looking for in the geological record in order to identify triple junction boundaries. I'm going to talk now just for a couple of minutes about where Metal Oceans is going, because it will never die. Metal Oceans was launched by Metal Earth, but it will have a life beyond Metal Earth. And one of the areas a couple of areas that we're thinking about are 2 settings. One is the birthplace of subduction, which is potentially relevant to the Abitibi Greenstone Belt, and the other is the syn to post-collisional margins of continents, and we'll talk about Papua New Guinea here in a moment. But we have started working on three locations really, where we believe the microplate edges are the location of subduction initiation. So subduction has obviously been going on here because of the advancing Pacific plate, but there are two locations at very sharp bends in the microplate assemblage. This one here and this one down here in the southern Fiji Basin, and another one up here in the northern Solomon Islands. And these represent locations. They're called step faults. These are subduction transform edge propagators, and these represent locations where the subducting slab is tearing and beginning to subduct below the overlying younger crust. And the two locations where we've been doing this, this is in the northeastern Lao Basin, which is the intersection of the Phonolai Rift with the northern margin of the Lao Basin and the subduction transform faults. And this is the location of the now famous Mata volcanoes, which are bonanite volcanoes that are actively erupting in the northern part of the Lao Basin. We see almost exactly the same mirror image of that down here in what's called the Matthew Hunter Ridge. And we have one student who is currently mapping the Matthew Hunter Ridge, which represents the easternmost limit of the New Hebrides Arc, where it is intersected by the back arc spreading center of the North Fiji Basin. And we have no arc volcanism going on anywhere along this segment of the Matthew Hunter Ridge, except right in at the interface between the spreading center and the older arc, where we have once again bonanite magmatism occurring here. So we're beginning to look at and this is the very early stages, beginning to look at what the initiation of subduction might have looked like and what role microplates might have played in that scenario. And then we're also have advanced our mapping now to include a significant part of the easternmost Papua New Guinea. This is a map that was published by our group, Philip Brandel, last year in Lithosphere. If you're interested in this, I encourage you to download the map, print it, and look at it. It's just the most spectacular thing you can imagine. And it basically has erased the boundary between the land, the continental landmass, and the oceans, so you don't see the shoreline anymore. And it's divided, this region has been divided into three large microplates, Woodlark, Solomon, and Manus microplate, together with an old four-arc sedimentary basin out the outer margin. The Abitibi Greenstone Belt, if you wanted to overlay it on there, would basically fit in a box like that. It could be any one of these microplate assemblies, but we're particularly interested in this one because that's where a significant number of the ore deposits occur. Here's a cartoon of that microplate assemblage. It's really a knot of microplates that's been caught between the advancing Pacific plate, which is stalled because of this large blue mass here, which is the Ongtong Java Plateau, and then the advancing Australian plate. And you've got about 10 microplates caught in this knot, which is about the size of the Abitibi Greenstone Belt. We're particularly interested in the this microplate edge, or this microplate margin, which is the northern part of the Bismarck microplate, because this is where all the seafloor hydrothermal activity occurs that some of you may be familiar with. This is the Nautilus Minerals property that was eminently going to be mined in 2019, but they went bankrupt. This is a back arc spreading center in arc-like crusts, so you're producing lavas which are very similar to, for example, Noranda, and large massive sulfide deposits. Out here in green and yellow is a four-arc sedimentary basin with as much as 7 kilometers of sediment. The distance here, you can see the scale, the distance between these felsic volcanics and the four-arc crust is about 75 to 100 kilometers, separated by very large scale, crustal scale transcurrent fault zones, this case called the Wheaton Fault. and several others that are subparallel to that. And then just on the other side of New Ireland, on the other side of this large crustal scale fault, is the world's largest epithermal gold deposit on the island of Lihir. This distance is about the distance between Noranda and Timmins, and you can easily imagine a scenario where you have rifting of arc crust to produce a Noranda-type volcanic complex and hydrothermal systems crossing over a large-scale transcurrent fault zones that are easily the size of the Destor Porcupine or Cadillac Break into a four-arc sedimentary basin, which could be Porcupine style with alkaline volcanoes, these black volcanoes poking up through the four-arc sediments to produce the world's largest epithermal gold deposit. These are the spatial and temporal relationships that we're trying to identify in metal oceans. And you can't say enough about the gold deposit. It's 60 million ounces. This is just a giant hole of gold on this one small alkaline volcanic complex on the island of Lihir. We've done a lot of work in this region, and there are offshore submarine volcanoes that are compositionally and metallogenically identical to the mineralization at Lihir, but at 1,000 meters water depth and active today, hydrothermally active today. Just to conclude, by way of illustration, this is effectively a triple junction. We have the subducting Solomon plate indicated by the red CMTs here, and we have the Waytun fault and the back arc spreading center of the Manus Basin indicated by the yellow or orange CMTs, and the location of Lihir is basically at the triple junction between those microplate boundaries. A lot of people have focused on this bend in the Solomon plate, which has an aseismic zone, a wedge of low seismicity in the three-dimensional view, plunging down immediately under the little dot there, which is the island of Lihir. The implication being that the slab is tearing and that has potentially contributed to the magmatic hydrothermal system that produced Lihir. We're mapping the surface features in the same area to see if that's it. Is that the only story? A slab tear under Lihir? It's way more complicated than that. And our last cruise looked at two features on the stalled Pacific plate, which are within about 5 million years of having subducted immediately under Lihir. One is called the Musau Ridge, which is probably an early and failed subduction zone. Another is called the Lyra Trough, this feature right here, which actually, this one is past Lihir already, but this one is exactly at the location of Lihir. And so now the implication is potentially we have two slabs, one broken, one torn, and these features being subducted immediately under Lihir. Chris's job, which he failed to do, was to generate a gravity model for exactly this location, but I guess there were some computer problems. This is the Bouguer gravity, which shows the island of Lihir, and you can see that there's something crossing the boundary between the Pacific plate and the New Ireland forearc immediately under Lihir that is not under the next adjacent island. So we hope we're going to see the gravity inversion of that, like tomorrow, maybe? Wednesday, okay. So just to finish, we're not done with metal oceans, and we're gonna carry this forward and look at a variety of other microplate environments around the world. Alan and a couple of other students are looking at completing this map here, which is basically Lao Basin plus Eastern Papua New Guinea plus the North Fiji Basin. But we're also looking at other environments. We're looking at the possibility of microplate generation by hotspot interaction, which we're doing in Galapagos and also in the Juan de Fuca. And Aaron is now sitting on this little spot right here looking at the possibility of, or the evolution of microplates in collisional zones. And all of this is a slide which I normally put at the beginning of the talk, but I put it at the end this time. All of this is to emphasize that we think probably a microplate framework is the best explanation for mineral deposit distribution in the Archean and the heat loss in the Archean. If you look at a model, a cartoon of what the Archean world might have looked like with as many as 35 or 40 plates instead of 12 that we have now, the cumulative strike length of all of the edges, the microplate edges, most of which or many of which are spreading centers, the cumulative length with 35 microplates is about 500,000 kilometers. That's compared to 50,000 kilometers of mid-ocean ridges that we have today. There's no better way to extract heat from the crust or extract heat from the mantle and generate hydrothermal systems. This is the actual projection of the microplate mosaic of the Western Pacific that I've shown you. This is an Antarctic polar projection which shows the actual clusters of microplates and larger plates that comprise the microplate assembly of today's Earth. And here's the same diagram showing the distribution of hydrothermal activity associated with those microplate edges. So we're nowhere near finished, but it was Metal Earth that gave us the launch. Okay.